gonna do this for a while. Before I start watching the videos. Some reason. For some reason I can't get beyond 130. I just got stuck at 120. Yeah, it's gonna take some time before I can get strong. I think I got it only once, 130. So I think I'm gonna watch this video first.
In the random forest. First, we will see why the random forest algorithm is better than our good old decision trees, and then I will explain how it works with visualization. If you want to see more videos like this, please subscribe to my channel and hit the bell icon, because I make videos
After I watch this video, I'm gonna go through this list here
about machine learning and data science regularly. So without any further ado, let's get started. To begin our journey, we need a dataset. Here, I am taking a small dataset with only 6 instances and 5 features. As you can see, the target variable y takes 2 values, 0 and 1. Hence, it's a binary classification problem. First of all, we need to understand why do we even need the random forest when we already have the decision trees. Let's draw the decision tree for this dataset. Now, if you don't know what a decision tree really is or how it is trained, then I would highly recommend you to watch my previous video. In short, a decision tree splits the dataset recursively using the decision nodes unless we are left with pure leaf nodes. And it finds the best split by maximizing the entropy gain. If a data sample satisfies the condition at a decision node, then it moves to the left child, else it moves to the right. And finally, it reaches a leaf node where a class label is assigned to it. So what's the problem with decision trees? Let's change our training data slightly. Focus on the row with ID 1. We are changing the x0 and x1 features. Now, if we train our tree on this modified dataset, we will get a completely different tree. This shows us that decision trees are highly sensitive to the training data, which could result in high variance. So our model might fail to generalize. Here comes the random forest algorithm. It is a collection of multiple random decision trees, and it's much less sensitive to the training data. You can guess that we use multiple trees, hence the name forest. But why it's called random? Keep this question in the back of your mind. You will get the answer by the end of this video. Let me show you the process of creating a random forest. The first step is to build new datasets from our original data. To maintain simplicity, we will build only 4. We are going to randomly select rows from the original data to build our new datasets, and every dataset will contain the same number of rows as the original one. Here's the first dataset. Due to lack of space, I am writing only the row IDs. Notice that row 2 and 5 came more than once. That's because we are performing random sampling with replacement. That means after selecting a row, we are putting it back into the data. And here are the rest of the datasets. The process we just followed to create new data is called bootstrapping. Now we will train a decision tree on each of the bootstrap datasets independently. But here's a twist. We won't use every feature for training the trees. We will randomly select a subset of features for each tree and use only them for training. For example, in the first case, we will only use the features x0 and x1. Similarly, here are the subsets used for the remaining trees. Now that we have got the data and the feature subsets, let's build the trees. Just see how different the trees look from each other. And this, my friend, is the random forest containing 4 trees. But how to make a prediction using this forest? Let's take a new data point. We will pass this data point through each tree one by one and note down the predictions. Now we have to combine all the predictions. As it's a classification problem, we will take the majority voting. Clearly, 1 is the winner. Hence, the prediction from our random forest is 1. This process of combining results from multiple models is called aggregation. So in the random forest, we first perform bootstrapping, then aggregation. And in the jargon, it's called bagging. Okay, so that was how we built a random forest. Now I should discuss some of the very important points related to this algorithm. First, why it's called random? Because we have used 2 random processes, bootstrapping and random feature selection. But what is the motivation behind bootstrapping and feature selection? Well, bootstrapping ensures that we are not using the same data for every tree. So in a way, it helps our model to be less sensitive to the original training data. The random feature selection helps to reduce the correlation between the trees. If you use every feature, then most of your trees will have the same decision nodes and they will act very similarly. That will increase the variance. There's another benefit of the random feature selection. Some of the trees will be trained on less important features, so they will give bad predictions. But there will also be some trees that give bad predictions in the opposite direction, so they will balance out. Next point, what's the ideal size of the feature subset? Well, in our case, we took 2 features, which is close to the square root of the total number of features, that is 5. Researchers have found that values close to the log or square root of the total number of features work well. And how do you use it for a regression problem? Pretty easy. While combining the predictions, just take the average and you are all set to use it for a regression problem. So that was all about it. I hope now you have a pretty good understanding of random forest. If you enjoyed this video, please share this video and subscribe to my channel. Stay safe and thanks for watching.
I was watching a podcast on Kurt Mongol channel. I subscribe to him on my other account. This last one here. And from what I understand, the guy says that you can find electromagnetic patterns in molecules, and just by emulating these electrical magnetic patterns, the cells, it's kind of like a software where you don't need to have the whole instructions. As long as you have, it's kind of like a it works like a similar way that the library works in programming. That if you have the electromagnetic pattern and you emulate that, the cells around it will create the object that is produced by that electromagnetic pattern. And I thought that was really, really interesting. So for example, if you take the electromagnetic pattern of an eyeball and you put it in the heart, then you don't need necessarily to know all the instructions to build an eyeball from the molecules. As long as you have that pattern and you implement the pattern, the molecules will figure out that they are supposed to build an eyeball in that place, and they will do that. And that's very interesting to me because it makes me think that everything is an electromagnetic pattern, and the way that things differentiate themselves is just by the configuration of electromagnetic patterns. And I was thinking about as well that an electromagnetic pattern or electromagnetic field is just a difference in the way that the layers of electrons and protons and all that stuff that makes up an atom is the configuration of that stuff in some region of space-time determines what the electromagnetic flow is. So it's pretty much essentially just the same thing. The only thing that's changing is the perception of the reference frame that is analyzing the portion of space-time that contains that electromagnetic field. And it probably works like a program in computer that, depending on the way that you arrange the electricity and the logic gates of computation, you have different softwares that perform different stuff along with the hardware. So yeah. made me think that everything works that way. It's just the same thing being shaped by different ways that gives the illusion that it's different than the other things, but it's just a manipulation of space-time. Not a manipulation, but a perception of space-time relationship to a reference frame. And then we give different names based on what we think that configuration is in relationship to the reference frame of human experience, which is data collection. So the obvious and biggest problem with that is that even though we can notice simple rules that make up this very complex pattern, it's probably unlikely that you can predict the complex pattern just by knowing the rules, like Stephen Wolfram says, that you can reduce computationally, even though the solar automata stuff, you can have very simple rules that create very complex behavior that is unpredictable. So the question is, how much of if you are able to encapsulate all the electrical patterns that make up the state of the system of space-time in a region in relationship to a reference frame, how much of that can you use to create a system that is anti-fragile in relationship to innovation, which is just the transformation of this electromagnetic field through space-time that is expressed in different forms. And I'm not sure how predictable that is. Maybe it is possible to predict how likely a form is likely to appear or to happen, but we obviously wouldn't know what that means because it's one of those things that you have to first have the shape in order to make conclusions of it, I think. But maybe it's possible to deduce implications of the transformation of this electromagnetic field in order to create systems and strategies that have the holistic view of the feedback loop systems that are interconnected that form the whole system. I'm not sure if I'm gonna watch videos on this. I think I'm gonna move on to the next topic. I'm gonna watch this video first because it seems
The universe is
has good visualization stuff.
full of stuff. Heavy stuff, light stuff, hot stuff, and cold stuff. But what about the stuff that you can't?
Oh yeah, so I think another topic that might be interesting to add here is chemistry. But I remember the basic stuff on chemistry, but
See or touch? How do you know that it's there? You can't.
I have to think about a more specific way of the thing that I'm trying to understand. Because I think the surface level stuff I already know and it would be redundant to watch videos about that.
Always count on your senses to tell you what's happening. I mean, what does seeing even really mean, anyway? Absorbing light with your eyes? But what exactly is light? We have a functional understanding of this strange part of everyday life that holds more mysteries than you would think. Understanding it would take centuries of scientific inquiry and research, and we're still trying to tie up the loose ends of some of the existing theories. That's what scientific research is all about. But even with the theories that we have, we've been able to create some amazing technologies with our understanding of the electromagnetic spectrum. The word photon is one that most of you have probably heard somewhere before by now, but what does it actually mean? A Google search will pull up a pretty comprehensive explanation, but that might be a little bit too comprehensive for general purposes. Let's see if we can simplify this wordy explanation down to something a little bit more intuitive. A photon is the smallest basic unit of all light. In vacuum, they travel at the speed of light, denoted by the letter c. The first one on planet Earth to discover photons was none other than Dr. Planarian Flatworm, or in his native language, Schmidti Mediterranei. Some biologists actually believe that the Cambrian explosion was started by the evolution of eyes, but this is still debated amongst biologists. Fast forward a few million years, and humans pop up on the scene. Figuring out what light actually was a scientific journey that would take hundreds of years. As discussed on this channel before, many great minds attempted to decipher the mystery of light. Newton was one of the first ones to make major breakthroughs in the area with the publication of optics. But the first one who would really come up with the mathematical form for light was James Maxwell. Electromagnetic radiation was calculated to have the same speed as light. This was not a coincidence in his mind. Light must have a similar nature to this radiation. But hang on, isn't radiation a bad thing? Well, as we'll learn, it's only high energy radiation that can be...
The main problem I have is understanding because logic and the configuration of the electromagnetic field seems to be entangled, in the sense that computation is the configuration of the electromagnetic field in relationship to a rule set, which is the rule set of logic. That seems to work, and that's how we operate, but then there's a hard problem of consciousness that is the barrier from which we can gain understanding through this paradigm, because logic is always a consequence of experience, so we can't use logic to define experience because it's born out of it, so to speak. And I think that's the issue. We're trying to understand computation through this paradigm because it's impossible to define where the rules come from using the rules themselves, I think.
A problem. The question...
But maybe this is relevant to the goal of creating systems that are anti-fragile in relationship to exponential attack in social systems, because it's probably possible that you can use the rules we have. It's actually the only way we have, from my understanding so far, of attempting to create systems that are anti-fragile, because everything we create operates from these rules, which is the scientific paradigm.
Question of how the sun's rays travel through
And
space
the logic of physics
to warm the Earth has been a question that scientists and philosophers have been pondering for ages. In the late 1800s, when Heinrich Hertz first set his hand to this task, he was already armed with the equations that James Maxwell had developed only a few decades before. Maxwell had predicted the existence of electromagnetic radiation by a fluctuating electric field, but Heinrich Hertz was the one who would actually prove it with an experiment and some physical evidence. To demonstrate the existence of this radiation, Hertz needed a way to generate it, but also to receive it and prove that it was there. It couldn't be seen, so another method needed to be developed in order to detect it. The very first transmitter and receiver was created by Heinrich Hertz. If his name sounds familiar, it's because the unit of frequency, or cycles per second, was named after him. Anything that oscillates, whether it be a pendulum, an electric field, or the air around you, has a frequency, how many times per second it repeats. The frequency of Hertz's radiation was roughly at 50 megahertz, or 50 million times in 1 second. The implication of his discovery was monumental, but he didn't really think so at the time. Another instance of a smart person making an incorrect prediction, or as I like to call it, famously wrong. But hang on, was he experimenting with photons or with electromagnetic waves? Well, to answer your question, yes. More theories would need to be in place to actually make sense of all this, and more scientists were constantly experimenting with other kinds of rays as well. The theories that would further illuminate the mysteries of the universe would be built on Hertz's proof. Hertz discovered the existence of radio waves with his experiment. He couldn't see it, but he proved that it was there with another coil across the room, completely unconnected. This was the first discovery of electromagnetic radiation, a type of energy traveling through space at the speed of light in the form of alternating electric and magnetic field. He didn't realize it, but he was creating fluctuations in what modern physicists call the electromagnetic field, an invisible ocean of energy surrounding us at all times. But Hertz wasn't the only one experimenting with rays of energy. Another physicist by the name of Wilhelm Röntgen was also exploring the strange nature of rays after the discovery of these Hertzian waves. He experimented with Crookes tubes, and after several experiments, he obtained an interesting result. He noticed that a new type of ray could shine through some materials. Photography was a new phenomenon in contemporary society, and using these ideas in conjunction, Röntgen created the first X-ray images. Unfortunately, though, the true nature of these X-rays were still unknown to scientists. The damages that the radiation was causing was mostly unknown to medical practitioners. Appearances of cancer were very common in people who had X-rays taken of them during this time, and it was only after decades of research that this effect was understood: ionization. Like all scientific researchers, Hertz and Röntgen were limited by the instruments, technologies, and theories of the time. Electricity was already widely adopted, but at this point, there was much unknown about about the atomic world. But the work that Hertz and Röntgen did to prove that these rays were of the same nature of light would lay the foundation for the future of science. It wasn't just proving that radio waves could transfer energy invisible to the naked eye. It was also that they did so in a manner very similar to how light did it, just at a different frequency. After the discovery of electromagnetic radiation, the scientific community attempted to understand the physical concepts around the light emitted from heated objects. This revolved around the predicted amount of light that would radiate from something known as a black body radiator. An ideal black body absorbs all of the electromagnetic rays that shine on it, regardless of the incident angle or frequency. If it were at zero temperature, it would be perfectly black. In a practical sense, everything is actually a black body radiator. Everything has an ambient temperature, and in Kelvin, it's actually pretty high. This effect can actually be most easily observed in metals by heating them up to sufficient temperature that they begin to glow. They get so hot that they emit light. The existing theory for the emission of light under classical physics was that such a radiator could continue to heat up, releasing higher and higher energy light until it began to emit ultraviolet light and practically turn invisible to the naked eye. This was according to the Rayleigh-Jeans law. Unfortunately, though, this was never confirmed by any experiments, and the experimental measurements that they would take diverged greatly from what they predicted. Max Planck was one of the physicists trying to understand this problem, and he took a slightly different approach. He hypothesized that the light was emitted in individual packets. Rather than a continuous stream of water, the light would flow as individual droplets. In the year 1900, Planck published his theory of Planck's law, which matched the mathematical theory with the empirical data much more closely. The foundation of Planck's law is regarded as the birth of quantum mechanics, and one of the greatest accomplishments of Planck's career. Thanks to things like the mechanized printing press, electrical communication, and a growing international scientific community, science was reaching unprecedented heights of knowledge.
So I think a good question that comes to my mind is, we can view society as the same way that we view molecules, which is just a configuration of the electromagnetic field. And the question is, where is the boundary that differentiates different molecules from other molecules, and how you determine that? I think that's probably has to do with quantum mechanics. So we have to understand the concepts of quantum mechanics in order to think about this in a better, more accurate way. And I think, yeah, all the systems we create are probably a consequence of this interaction. Just like if you imagine politics, you're always going to have left and right because they exist in relationship to each other. And I think that's how the electromagnetic field works as well. It's always symmetrical because the distinction happens when you have an observer and what's being observed, which is the dualistic nature of the universe that comes as a consequence of identity or an ego structure. So it's always a convergent multifractal symmetry because it repeats the same pattern at different scales, but is always the same relationship of this polarity between things, the yin and yang. And although it's different in energy, in geometry, because negative charges and positive charge are not equal, but they are always symmetrical in the relationship of the polarity itself. So I think that the structure of societies is a geometrical structure in space-time that is a configuration of an electromagnetic field. And the question is, how do you determine this boundary on space-time? Because you have to think that it evolves over time, and that's a problem of entropy and having this idea, a notion of past and future, and assuming that the future is always a consequence of the past through the laws of physics. So if you were to take all the possibilities for the evolution of mankind, what would be that four-dimensional space, and how do you determine what's more likely to happen given the four-dimensional space with the current electromagnetic field? Because I assume it's probably like a game tree. If the notions of the laws of physics we have so far is accurate, which is that the past is classical and future is quantum, because observer and what's being observed is a quantum entanglement that follows the wave function. I think that's the current paradigm at least, but I'm not really sure.
I think that these factors actually made it possible for Albert Einstein to become involved in science. When he published his papers in 1905, Max Planck was one of the first to recognize just how important the theory of relativity was. But Max actually disagreed with Einstein's concept of a light quanta, or what scientists now call a photon. Over time though, as you can tell, this theory became generally accepted. And actually, after the idea that light appeared to have the property of wave-particle duality, one scientist wondered if other objects in the quantum world could share that property. Louis de Broglie founded the theory of the electron wave. He proved...
And also, another thing that comes to mind is that you can view market dynamics as being a reactive system in relationship to the environment that works less like a homogeneous works, where you have the utility of things being computed in relationship to the decentralized system that a market economy is, which is the relationship between the limbic system and the prefrontal cortex, where the consumer is the limbic system that determines what's going to be produced, and the prefrontal cortex are the structures or things that are being built in order to serve that limbic system. So I think that there might be a relationship there with the configuration of the electromagnetic field and the momentum of the market economy. And maybe we can't predict it's possible to predict the way that the electromagnetic field is going to change, which is the entire universe, but it might be possible to predict what's the response is going to be from human beings, because it follows it follows a fractal pattern, which is the way that the limbic system relates to the prefrontal cortex. That's what I think.
Proved that electrons actually shared a similar duality that light did. In some circumstances, it behaved as a wave, and in others, a particle. It just depended on the context. The theory of the electron wave is actually quite important in modern times, because most graphene devices use this theory in the design phase. For the most part, these devices are found in cutting-edge scientific research, not really found in everyday life. But the cutting edge of scientific research builds upon the work of all of these great scientists, and over the course of just a few short decades, these scientific advancements have led to leaps and bounds in technological development. In the 21st century, we have many different ways of taking advantage of ripples in this invisible ocean of energy that exists on both sides of our narrow band of visible light. Radios, routers, smartphones, Bluetooth, all of these take advantage of lower energy radiation. Streams of these photons will just gently wash over you, gently rolling over you like a wave in the real ocean. The electric and magnetic fields will just pass through you, usually with no ill effect. However, when a ripple in this invisible ocean becomes more powerful, this is when a problem can occur. Rather than washing over you like a gentle wave, they basically slam into you like a fire hose. The term ionization actually refers to the formation of ions by these high energy photons. They have so much energy that when they hit the molecules that make up your body, they unbalance the stable bonds that hold the molecules together, changing them from stable atoms into ions, charged atoms. This effect only lasts a few microseconds as the charge neutralizes, but the change to the molecule can be an extremely serious problem for the overall function of the cell. If a cell's DNA is changed, it can change the way the cell reproduces. This is how radiation can cause sickness and cancer. But remember, it's just the stuff on the high energy end of the spectrum, usually emitted by what we would call radioactive objects. These objects are still emitting gamma radiation because they've been energized by some source. But in most people's lives, this isn't a problem that we have to deal with very often. Most everyday applications just use the stuff on the lower energy end of the spectrum. Even the MRI machine uses a specialized radio coil for capturing its images. But I think we've covered enough for this time. I hope you enjoyed the video, and I'll see you next time. This has been your Everyday Engineer, signing off.
The biggest challenge is the problem of the boundaries, in my mind, that it has to follow the laws of gravity. These things have to be related with gravity and the electromagnetic field, because they are what determines what the boundaries of things are. But then it becomes a question of philosophy, of the epistemology of science, and the identity of things, and consciousness, because the boundaries also depend on how you perceive things, and what determines the scale of perception from which experience is being born. That's the biggest question, I think. So I think I'm gonna watch a few more videos on this, and then I'm gonna watch videos about what defines power. I think I need to be a little bit more specific. But probably there will be no videos about this because, yeah. Maybe there are papers or scientific papers or other stuff related to this, but I think it's hard to believe that there will be videos about this. Because in my mind, the way that power works is a polarization. It seems to be, but I'm not sure. I think this might be because it's a consequence of the way that market dynamics happen, because it naturally polarizes things in order to capture more power and control. That's the way that the limbic system incentivizes the prefrontal cortex to behave, because it's a binary system of zeros and ones, and it doesn't understand context really well. So there's a delay of the limbic system to reality, and the function of the limbic system makes the prefrontal cortex polarize the system in order to gain power. And this is not the best strategy, probably. But I'm not sure if power is exactly that or something else. Because it also has a property of increasing the influence that a region of space-time has on the row itself. It's kind of like gravity, in a way. Where the more power you have, the bigger the implication of your decisions become. So I think there might be also a correlation between power and gravity, or density, I should say. But how do I find that correlation? Is the question. And I'm not sure if it's exactly that I'm thinking, or might be something else. What increases the power of someone in a social structure? So I need to think about the principles that involve this question so I can understand. Because if I just ask the question, I don't think there will be an answer, but maybe if I think about the principles, there will be a way to increase my understanding and try to derive an answer based on that. So we can view power as capturing the limbic system. So power, in a sense, through the market economy, is polarization, because that's how you capture the limbic system. Because the limbic system is unaware of the context, and that's the problem. It's kind of like a battery where the prefrontal cortex understands the context and is in function of the limbic system, but it also understands that it can't be trapped by that. And that's where regulations comes in. So yeah, I think you can say in a market economy, power is polarization. And the regulation of that polarization is also done by the markets, because there needs to be an incentive in order for something to be regulated. But the way that the incentive is created for the regulation is different than the way that it is created by consumers, I think. So I think in a sense, even though it's both ways work by the market economy, the regulation is also partially defined by the prefrontal cortex of the whole, because yeah, people get the sense that something is off by analyzing the context and exchanging ideas, and that creates the momentum for regulation to happen. So you can say that power is the polarization that happens when consumers incentivize the capture of the limbic system by the prefrontal cortex, by incentivizing institutions to build things that will make everyone addicted so they can gain more power and control. And that increases the influence that those institutions have on the environment, which then creates the incentive for the markets to regulate the institutions that were built. So it's kind of like a gateway feedback loop system where I have the flow from the limbic system through the market economies that produce institutions that create things, and then you have the flow back where this creates a reactive response that adapts the system again based on the regulation, based on the what's being built. So I think in a sense it works through, I don't think power is directly correlated to polarization, but I think in relationship to market economies, it probably is a consequence of that. Maybe. Actually, I'll do it like this. I change the size this stuff. You can see her. Yeah, the limbic system over here. And go to the market. It's pretty bad, but then this becomes institutions. Then these institutions go through the limbic system again. Maybe it's not limbic system. I think both of these is prefrontal cortex. But there might be other stuff from the brain that I'm not familiar with that makes the gap between the two. And then this activates the market as well as a reactive response. Which then go through the limbic system, closing the feedback loop. I think that's how it works. On a very simplified way. And this structure is an electromagnetic configuration that dictates the shape of social structures in relationship to an environment based on the adversities that the environment brings. I'll be right back. So another idea that came to my mind is that, well, first, this is where the internet comes in. The internet increases the acceleration of the cycle, which makes the asymmetries more visible. But what's an advantage for humanity and also a disadvantage is that this cycle is not synchronized with the environment. And I think that's why we dominate other species, because the environment can't regulate the cycle, because the expansion is always happening faster than the regulation. This might be not accurate, but so this part of the cycle happens faster than this, and that's why it grows. Because by the time you have enough momentum and force to regulate the stuff that is created, there's already more stuff being created. So you can never regulate what the innovation is doing. And the more you increase the acceleration of this cycle, the more visual becomes the asymmetries in the system. And that's what the internet does. The internet increases the flow of electricity and information, which changes the shape of the electromagnetic configuration of social structures faster, because it increases the velocity and capacity of the computation of markets, because that's what the human brain does, I think. But that capacity is distorted because in order to gain control, the prefrontal cortex had to polarize the system. So it polarizes in order to capture the limbic system through markets. This creates a skewed perception of what reality is, which creates a skewed perception of what the regulation might be for this thing, because you can't have nuanced regulation at scale with human beings because of the lack of data and accuracy, and because of the nature of corruption that happens at large scale. So every time you have a nuanced situation, both sides will try to exploit to their side, and because you can't apply the scientific paradigm to create a law that is going to be nuanced, you can't. You need to have binary regulation systems that are inefficient. Which only increases the asymmetries of power and control of the system, and then this is what eventually leads to the collapse of the society, I think. So the question is how, I think the way to solve this is thinking about how do we make the cycles symmetrical, where we have a very efficient regulation system that is synchronized with the expansion of markets. And maybe we have to change the way that we create stuff, we compute, so a different system that is not a market economy. And we have to think about what that will look like. So what I have to think about is how how markets are imbalanced, I think. Why do they do computations that don't seem to be aligned with the long-term vision of what would be a more stable structure for everyone? And the factors are at play at probably the electromagnetic field of space-time, because that's what shapes the incentives. and how we define who deserves to do what, I think. Because the whole point of having a market is so that you don't put on subjectivity because of the cycle of corruption of human nature, that leaders will become leaders because of how confident they seem to be in certain ideas, which makes the system flawed. To have an aristocracy, and the way to get out of that is to put the responsibility on the abstraction, which is the market, so that nobody can argue, because you have what people believe should be facts, but as we know now that there is no facts, and it's just pushing the problem one step further, which is now you have markets that corrupt the information system and the scientific community in order to push agendas by formulating and framing different data based on what they want to be pushed. And then you have the competition between them in order to control this information and in order to get more power, which leads to polarization and lack of common sense. That is exemplified by power and by the velocity of this flux of the cycle here. So I'm trying to think, what would the better system than the market economy would be? I think the question is, how do you find a way to define what is important for long-term stability of the system? So one of the challenges, you can't predict innovation and how that's going to impact the system. The other one is that we probably will never have enough accuracy to determine the correct boundaries to create nuanced rules at scale that can regulate the system efficiently. Because once you get into subjectivity, both sides of the disagreement will try to use information to push their agenda, and you can determine through facts which side is correct. So the only way to prevent that would be to gather a bunch of data and monitor everyone, so we have perfect information across the whole spectrum of humanity to know what happened at any moment in time. And then you can use that information to draw nuanced lines, but I think this is clearly not a very good future for everyone, because it would mean that everything is monitored, which is the direction we are heading towards, I think. So there must be a way to regulate the system without having perfect information. So I think one question I could ask is, what is the frequency? Yeah, I would have to think about how to answer this question. But what is the frequency of innovation in market economy? Also have to think about credit because credit is a tool that amplifies the power and further increases the asymmetry of information and control because the rules get corrupted by money, which is using credit and more power in order to increase the gap of the asymmetry. So I don't think it is that important because it doesn't change fundamentally the way that structure works. It just amplifies the velocity in the same way that, but it might be because this has an impact on how important it is to increase the velocity of regulation as well. We can think that there must be a direct correlation and direct inverse correlation between the increase in technology and power and the velocity of regulation that is needed in order to have a stable system. So if technology advances exponentially, we need a system that is capable of regulating itself exponentially as well, which means it's faster than all the bureaucracy of governments, but at the same time can't be corrupted by human nature, which is the tendency of the limbic system to minimize energy and avoid risk. That makes people want to follow the easier path and either consciously or subconsciously by telling lies to themselves and shifting the rules slightly more towards their side instead of looking at the whole picture and how everything is connected. Also because lack of information and understanding. So how would I be able to measure this? What type of data do I need and how can I get this data? There's also the question of what comes first, the need for a product or the study of what a need would be. Because like the cell phone, I think the cell phone came before people thought they would need the cell phone. So there's also that, which sometimes the incentive comes as a byproduct of the engineering in order to achieve more power. So people study market behavior and consumer behavior, and then they create metrics to create products that they think will appeal to consumers with even without them knowing that they would want that product. So I think I need to figure out a way to maybe I have to study the limbic system. I need to study the limbic system more, I think, in order to create a better picture of how it works. Rate of response in limbic system. So basically, limbic system generates momentum through gravity and identity that generates the force of markets to change reality, I think. So I think, yeah, the limbic system might be connected. Yeah, is obviously connected, but it has some momentum through the identity of people as well. that momentum of society overall makes the changes in the structure. So the question is, how long does it take for the stimulus? But the issue is that's much more complicated problem because it involves abstraction and identity and groupthink. So yeah, question might be, how long does it take for individual limbic systems to gain coherence by forming a group? Maybe I can study the recommendation systems in order to find that. So yeah, I think that's a great idea. So how long does it take someone that gets involved or engaged in a recommendation system to change their belief structures in order to fit into a group? And I think this would give the greater frequency of the synchronization of limbic systems. And then once you have that, you can probably create a model of social structures. There's also a question of hierarchy as well, because every group is going to be hierarchical by definition because of entropy. And the way that hierarchy is shaped might be also connected with the market dynamics. Because you have thought leaders. So yeah, another thing to think about and try to understand is how the hierarchy is formed. What determines the position of each person in the structure? I have to think about that. Right back. I think I have an idea of what I was talking about before, which is that innovation happens at the boundary of knowledge and of new information. So social structures are like neural networks applying a loss function to new data through the market economy, and that flow of information, what gets adapted first is the people that are at the boundaries, which you have a lot more risk when you are at the boundary because there's a lot of more uncertainty, which means you can be either crazy or genius. And then the bulk mass is formed on judgment because they have that's the way that you stabilize the system is through morals. So you have this flow of information where that's why you have as the first reaction to people bringing new ideas, you have a lot of resistance to change because that's what defines the structure of the system. And I think that it might be possible to map out of the flow of information through certain personality types that determine how the structure is going to be given a certain incentive structure, incentive system. So in relationship to the market economy, you're going to have certain personality types that are going to be responsible for the innovation, which are going to create the flow and flux of the hierarchy of the social structures in relationship to new data coming into the environment. So if we're able to gain data about the flow of this structure, the way that the groups are formed, I assume that the people that come first and create the groups first, they have a lot more risk, but they are gonna be the leaders, and then the people that adapt last are the followers. So there might be a connection. There probably most likely there is a connection between the different parameters of the brain, the size of the limbic system, the amygdala, and the prefrontal cortex that determine how fast is the adaptive behavior of people and how much risk they're willing to take and to form the systems. And it's always going to be in relationship to the way that the economy is structured, because that's how this incentive structure is built. So the market economy incentive structure incentivizes, at least it seems like sociopathy should be one of the main personality types that is responsible for creating the shape of the social structures, which causes the lack of alignment between social structures and the environment, which causes the imbalance of the regulation through the vicious cycle of corruption that happens because of the nature of the limbic system to try to always go for the path of least resistance and rationalize its behavior. And that gains momentum because the identity and gravity. So maybe by studying the cycle, you can try to imagine different systems that have different rates of adaptivity that would create different structures that are more stable. So basically, I think the market economy overfits the data by incentivizing certain personality types that don't have holistic thinking to be rewarded first because of the nature of the arms race. But the question is there enough data and is the data accessible to make a study of all personality, all different brain shapes and personality types? Uh, Create the geometry of social systems in relationship to space time through the lens of markets. So markets are kind of like a gate. Here you have a bunch of people, then this is the markets. And because they're shaped like this, and the structure by genetic mutation of personality types in social systems, you're going to have a certain flux here. It's going to be like this. And this flux is going to create the structure at the end, whatever that structure is. And this is a constant feedback loop because there's always new information getting into the system. And that's why there is this loop, is to fit in the new information with the system. If I'm seeing this the correct way. And then if it's possible that if you change the incentive structure, then the final shape would be different. And the question is, what is the shape at the end that is anti-fragile in relationship to exponential tech and the flow of the electromagnetic field that surrounds social structures at any given time. So I think I'm gonna go back to watching these videos.
In an electromagnetic wave, why are the electric and magnetic fields both at their maximum at the same time and at the same place? The fact that the electric and magnetic fields are in phase with one another is a counterintuitive result. After all, Maxwell's equations state that it's the rate of change of the electric field that induces the magnetic field. And the rate of change of the electric field is at a maximum when the electric field is zero. Similarly, Maxwell's equations state that it's the rate of change of the magnetic field that induces the electric field. And the rate of change of the magnetic field is at a maximum when the magnetic field is zero. So, why are the electric and magnetic fields not out of phase? The key to the answer is that Maxwell's equations relate the rate of change of each field to the curl of the other field. The blue arrows describe a vector field, which we will call F. The orange vector is the curl of F. As the vector field changes, the curl changes as shown. Let's set 2 of the 4 field vectors to 0. As the 2 remaining field vectors change, the curl changes as shown. The curl is 0 when the 2 neighboring field vectors are of the same length and are pointed in the same direction. The curl is at a maximum when the 2 neighboring field vectors are pointed in opposite directions. Let's keep this in mind when analyzing the curl of the electric and magnetic fields of an electromagnetic wave. Let's take our electromagnetic wave and consider just one moment in time. The curl is at a maximum where the field is 0, which is where the neighboring fields to the left and to the right are in opposite directions. The curl of the magnetic field is directly proportional to the rate at which the electric field is changing. Let's now consider the curl of the electric field. The curl of the electric field is equal to the negative of the rate at which the magnetic field is changing. Hence,
I think I already understand this.
In this video, I'm going to show you a mind-blowing example of the connection between the electric and magnetic forces. You're going to see exactly why magnetic fields are generated by moving charges. Let's quickly go over the basic facts. Naturally occurring magnetic materials were known to the ancient Greeks, and by the 12th century, the Chinese were navigating using compasses made out of magnetic lodestone. From a modern perspective, we would say that the compass needle was aligning with the Earth's magnetic field. The magnetic field is an abstract way of thinking about the force that a magnet exerts on other magnetic materials or on charged particles. The motion of the interior of the Earth generates a magnetic field, and this magnetic field protects us from harmful radiation in space. The Sun emits a number of charged particles, for example electrons and protons, and these are deflected by the Earth's magnetic field, away from causing harm in the lower atmosphere. The magnetic field produces a force on moving charges. A stationary charged particle will not feel a force from the Earth's magnetic field. We can see this from the mathematical expression of the force. The force is equal to the charge of the particle, q, times its velocity, times the strength of the magnetic field, b. So you can see that the larger the velocity, the larger the magnetic force. And if the velocity was 0, then, well, the magnetic force would be 0, because the force is proportional to the velocity, and therefore a stationary charged particle experiences no force from the magnetic field. In contrast, the electric field acts on any charged particle, whether they're moving or not. Our experiences with the electric force began even before we knew about magnetism. Ancient peoples knew that rubbing an amber rod with cat's fur would cause it to attract other objects around it. We now know that the process of rubbing the amber rod with the cat's fur is transferring electrons from the cat's fur onto the amber rod. And so the amber rod gains an excess of electrons, and since electrons are negatively charged, the amber rod as a whole becomes negatively charged. The cat would become positively charged. And again, we've invented this abstract idea of the electric field to help us describe the forces that a negatively charged or positively charged object exerts on the charged particles surrounding it. Because this amber rod is now negatively charged, it's going to attract positively charged particles. So a proton that's just sitting in empty space is going to be attracted towards the rod. Even if the proton were moving, its motion would be bent towards the rod. An electron would feel a force away from the rod, and so its motion would be bent away from the rod. And again, we have a simple expression for the force produced by an electric field. The strength of the force of the electric field is equal to the charge of the particle multiplied by the magnitude of the electric field. But until the 19th century, we didn't know that there was a connection between these two forces. Sure, they both acted on charged particles, but electricity was produced by the action of rubbing two objects together, and magnetic materials were dug out of the ground. It was a man named Hans Christian Ørsted who provided the first evidence that the electric and magnetic forces were connected. And he was performing experiments on electric currents. In order to produce an electric current, you create an electric field in the wire, and you usually do this using a battery, and this electric field causes the charged particles in the wire to move. In the case of a metallic wire like copper, the positively charged particles are the nucleuses of the different copper atoms, and these form a lattice inside the wire, a rigid lattice, so these particles can't move in response to the electric field. They're fixed in place. But the electrons that surround these nuclei are free to move, and so the electric field is able to move these electrons, and the movement of the electrons is called an electric current. And it's the same electric current that delivers power to your household appliances. And Ørsted discovered that if he held his compass next to the wire, the needle of the compass was deflected when there was an electric current flowing. So the electric field in the wire produces a current, and the current, in turn, produces a magnetic field outside the wire. And because it's a magnetic field, that means it's going to interact with any moving charged particles near the wire. So if a proton is moving parallel to the wire, in this case it's going to be deflected towards the wire, and if an electron is moving parallel to the wire, well, it's going to be deflected away from the wire. And this really was a huge discovery that led to a flurry of results that explored this connection, the connection between the electric field and the magnetic field. And this research eventually culminated in Maxwell's equations of electromagnetism. And Maxwell's equations give you a formula for how the magnetic field changes in response to an electric field, and how an electric field changes in response to a magnetic field. But it doesn't tell you why they do it. The actual mechanics behind the relationship between the electric and magnetic fields is incredibly surprising and at the same time very beautiful. Maxwell's equations were the inspiration for Einstein to produce the theory of special relativity, and actually it's special relativity that hides the secret that is the connection between the electric and magnetic fields. For those of you that know special relativity, this could come as a big shock because special relativity is a theory about objects that are moving very fast, and in our case, nothing appears to be moving very fast. We have a current in the wire, but the electrons moving through the wire under the influence of the electric field are actually moving very, very slowly. And even the charged particles passing by the wire are moving at mundane, everyday speeds. Nothing is traveling anywhere near 10% of the speed of light, which is really the threshold where we need to start using special relativity. But by the end of this video, we're going to derive an equation that describes the magnetic force on a charged particle moving near a wire using only the formulae of electrostatics. That's the electric field produced by static charges, and special relativity. And given that we can find our answer using special relativity, what's the first thing we're going to do? Well, we're going to transform ourselves into the frame of reference of the particle which is experiencing the force. That means that we're going to start moving so that we're alongside those particles moving outside the wire, and we're going to try and see what's happening from their perspective. So once we start moving at the speed v, which is the speed our proton and electron are moving at, well, they're
Right back.
they're going to be stationary. And the positive ions in the wire, well, they were stationary before, but now we've started moving at the speed v. They're going to be coming towards us at that same speed. So it appears like all the ions in the wire are going to be rushing towards us at this speed v. And what about the electrons? Well, they were moving at the speed v0 towards us originally. But now that we've started moving at speed v as well, then surely the speed they're coming towards us is just v plus v0. But actually, this is where it gets a bit tricky because special relativity takes us outside the realm of our everyday understanding of time and space and velocity. And special relativity tells us that the velocities of objects don't add in the simple way that we think they do. For example, if the particles on the outside of the wire were moving at some crazy velocity, like 3/4 the speed of light, and the particles inside the wire were also moving at 3/4 the speed of light, then when we add those two velocities together, we get something that is 1.5 times the speed of light. But the whole premise of special relativity is that nothing can travel faster than the speed of light. So it necessitates that adding velocities doesn't happen in the usual way. And instead, if we want to add two velocities, in our case v and v0 together, we need to scale the resultant velocity. It's easier if I just show you the formula. The actual velocity that will be produced is v plus v0 divided by 1 plus v times v0 over c squared, where c is the speed of light. Ordinarily, when v and v0 are very much smaller than c, then the number in the denominator, 1 plus v v0 over c squared, is going to be very, very, very close to 1. And so the velocities will appear to add in the normal way. We'll have some answer that's very, very close to v plus v0. There are some other weird properties that special relativity introduces. So what are these other weird properties? Well, the first is that the force due to the electric field experienced by our charged particles is different depending on whether we're moving alongside the particle. That means we're in the reference frame where the particle is stationary, or whether we're watching the particle move by us. That's the frame of reference where the positive ions in the wire are stationary. And the ratio of those two forces is given by something called the Lorentz Factor. And the Lorentz Factor is a very important parameter in special relativity. Things like space and time, when we start to move very fast, are squashed and stretched by this factor gamma. And so it is in the case of the force provided by the electric field. If we measure the force as we're moving alongside the particle, and then stop and stand still and watch the particle whiz by, and then measure the force that we've measured the second time is going to be a factor of 1 over gamma times the force we measured when we were moving alongside that particle. And I've already mentioned the other strange fact that we need, and that is that once we start moving, the distance between objects gets squashed, space gets squashed, and space gets squashed again by the factor 1 over gamma. So that means that suppose my table has a length d0 when I'm sat in front of it. As soon as I start to move past it, the length of that table is going to shorten a little, and the length that I'll measure as I'm moving past it, which we'll call d, is going to be equal to the original length, d0, divided by the Lorentz factor, gamma. And since the Lorentz factor is always going to be greater than 1, then the new length we measure is actually shorter than the length we measure when we're sat next to the desk. And this discussion applies equally well to the particles in our wire. So supposing the positive ions are a distance apart d0 when we're sat next to the wire, when we start moving at the speed v alongside the charged particles, we're going to be moving past those positive ions. So the distance between them is going to appear smaller than it was before. And it's going to be smaller by the factor 1 divided by gamma. And the same is true of the electrons. But the electrons are moving at speed u, and u is faster than the speed v. So the electrons are going to be squashed together even more. And the distance between them, instead of being d0, is going to be d0 over gamma of u. Oh, or is it? Because actually, if you think about it, when we were sitting next to the wire, the electrons were already moving. And so because of that motion, they were already closer together than they would be if they were stationary. To find out how close they would be together if they were stationary, we need to multiply by gamma instead of dividing by gamma. So that means when stationary, the electrons would be d0 times gamma of v0 apart. And that's the number that we need to divide by gamma of u to find the distance between them when we're moving along at speed v outside the wire. So can you see that because the distance between the electrons is now less than the distance between the positive ions, then there's an overabundance of electric charge in the wire. There's more electrons in the length of wire than there are positive ions in that same length of wire. And so we have a situation exactly like we had with the amber rod. Our length of wire has more electrons than it has positive ions. And so when we're moving alongside it at the speed v, it appears negatively charged. And we know that a negatively charged object has an electric field, and the electric field lines point in towards the center of that object. And so if I were a proton moving alongside this wire, I would be attracted towards it because the wire is negative. And if I were an electron moving alongside the wire, I'd be repelled away from it. Since we're also moving at the same speed as this electron and proton, they're just going to move towards and away from the wire. But if we're sitting in our stationary frame and we see these particles go past, we're going to see them either bend towards or away from the wire, and we're going to say that they've experienced a force due to the magnetic field produced in the wire. But if we were to move alongside those charged particles, alongside the electron, alongside the proton, we'd actually see the wires not having a magnetic field, but having an electric field, because the wire would appear negatively charged to us. So here is the really deep connection between the electric and the magnetic fields. A particle that appears to be influenced by a magnetic field is actually just experiencing an electric field. Isn't that great? What a beautiful connection between the electric and the magnetic fields. And who'd have thought that it would be special relativity that holds the answer? Now, some of you might not take my word for it. And so we're actually going to derive the force on these charged particles. It's going to involve gamma of u. Well, we know after a little algebra, you'll see that we get 1, but now we need to use our new simple formula to find out by 1, lambda is going to be equal to strength of an electric field for a log to the current in the wire over 2 pi r, all times v. And that's exactly the formula.
I think I already understand this. After I watch these videos, I think I'm already gonna start the playlist and I'm gonna try to code this stuff. It's probably the most useful thing I can do. I might research if there are libraries of physical equations first before I start coding things. So I don't waste my time.
As a famous Swiss man once said, man is born free, and everywhere he is in chains. This short quote goes to the heart of one of the central phenomena of study within the social sciences, that is the idea of social order or structure and its relationship to agency, freedom, and the capacity to change this social structure. Social institutions provide the paths and roads in our lives. They are the default positions that have already been created. They are the established institutions of culture, politics, and the economy that enable us to go further, faster, easier, to do more. They enable us, but they also constrain us, and they are the frameworks through which power is exercised. When we take these pathways, we give over our agency and choices to travel along roads that have already been created by someone else. Someone else is defining our choices along this path, and in so doing, they have power over us. In the social sciences, social structure is the patterns of social arrangements in society. They are both emergent from and determinant of the actions and relations between agents. As enduring patterns of behavior and interaction, they define some form of order to the overall system. Social structures are typically complex and recurring patterns of organization. In contrast to social structure, social agency is the capacity of individuals to act independently and to make their own free choices. Because social structure is largely about order, it is often treated together with the concept of social change, which deals with the forces that change the social structure and the organization of society. Structures are really designed to facilitate order, but social change requires some form of individual initiative. So we have to ask, how do we as individuals change the social structure around us? Here, we see the interdependency between the two. We need structures that often constrain the individual, but also we need individuals in order to test and change the structure so that it can develop. We need order, rules, obedience, and the structure that they bring, but we also need individuals who will sometimes break and test those rules in order to make them manifest and so help to develop them. Social structures or organizations are a product of agents coordinating their activities in some fashion. This coordination can only happen by the individuals giving over their agency, their choices and actions to that organization. In people giving over their agency, they allow the organization to make decisions on their behalf. They submit to following orders and become obedient to the organization's agenda. Without this submission and coordination, we have no form of structure. It is only by police officers following orders that we can incarcerate people. It is only by people choosing to go to work every day that we get business organizations. It is only in our collective belief in money that it has any value. So the real question is then, why do people give over their agency to organizations? Sociologists have really found 3 answers to this question. We do it either out of coercion, meaning we give up our choices because of the force that others exert on us, or we do it in exchange, meaning that we bind ourselves into organizations because we perceive the benefit to us to be greater than the cost. Or lastly, we do it for normative reasons, meaning that we form organizations and maintain them because we see it as a process through which to achieve some collective outcome that we value. Each of these different bases for giving over our agency create very different social structures with a different process of change, so we'll go over each of them separately. Coercive organizations are driven by relations of conflict. Military dictatorships are a classical example of coercive organizations. Power is based on force. You give over your agency because, ultimately, of some fear that you have. As humans, we actually use physical violence very rarely in our interactions. Actually exercising violence is often a very last resort. What we do use, though, is intimidation, displays of power, manipulation, propaganda, neglect, acts of omission, etc. that are ultimately all trying to force one into adopting certain actions, and out of this, we get some form of order and organization that is based on coercion. Inherent to the conflict theory of social order is that conflict is the normal state within a society, not the exception. This is most famously captured by Thomas Hobbes' book The Leviathan, where he posits that man, in a state of nature, is in a continuous war of all against all. Order is then seen to only be maintainable through some powerful in order to agents on the lower levels of the organization through conflict.
This is not gonna have anything useful, to be honest. Just gonna talk about basic stuff.
Every day of your life, you move through systems of power that other people made. Do you sense them? Do you understand power? Do you realize why it matters? Power is something we're often uncomfortable talking about. That's especially true in civic life, how we live together in community. In a democracy, power is supposed to reside with the people, period. Any further talk about power, and who really has it, seems a little dirty, maybe even evil. But power...
Alright, this thing is also gonna talk about simple stuff. Of state action, blah blah. Yeah. I think it might be that the definition I'm looking for is just the entanglement. It's not that the decision changes more the space, it's just that it acquired more momentum of the electromagnetic field. The density might be equal to power, gravitational force. Yeah, but the question is how does certain electromagnetic configurations have more influence over space-time than others? It might have to do with the state of the molecules. I think that I'm gonna start with the tensor stuff. It might have to do with radiation or something like that. Or fusion, or fission and fusion. That it takes more or less energy to break apart or connect particles. So understanding that maybe the same as power, which goes back to space-time and gravity.
We need to discuss how force is related to potential energy. Let's start that discussion by assuming we have an object.
I'm gonna put here I think I need to study NumPy to be able to compute the tensors. So maybe the free code camp playlist on NumPy is gonna be good to revisit.
It moves along the x-axis from some initial position x equal a to some final position x equal b while subject to a net force along the x-axis called F sub x. Let's further assume the force may vary according to the position of the object. We indicate this by making the force a function of the x-coordinate of the object. The network due to displacement in the x direction, W sub x, is computed by multiplying the force by the differential displacement dx and integrating the product from the initial position x equal a to the final position x equal b. The network in the x direction is also equal to the change.
Another thing that I'm gonna look for is library Python for physics equations. Are there any good up-to-date physics libraries for Python that are for Linux? Just gonna into Python. PyMonk is another promising one that you might want to take a look at. PyPyOld is the Python binding of Open Dynamic Engine. Basic physics kinematic equations are all you need. Then the questions was already answered. So it seems there is a library which contain the simulation sets gravity. Installation overview, API reference. Source repository. So that's one. I think there might be more.
change in kinetic energy of the object during the move, which is 1/2 the mass of the object times the square of its velocity in the x direction at the final point, which is b, minus 1/2 the mass of the object times the square of its velocity in the x direction at the initial point, which is a. Note that we are using u for velocity. In short, if an object experiences any change in kinetic energy when moving between 2 points, net work has been done. We will be particularly interested in systems containing objects that are exposed to forces that depend only on the position of the given objects. These types of systems are called conservative systems, and they involve no forces that cause the mechanical energy of an object to be changed into other forms of energy such as heat or sound. Another way to say this is that conservative systems involve no dissipative forces such as friction or air resistance. Examples of conservative systems include objects in gravitational fields and objects in electric fields. A gravitational field, such as the Earth, forms a conservative system because the force on the object depends only on its position relative to the surface of the Earth. The Moon remains in orbit about the Earth because the gravitational force creates a conservative system. A requirement of a conservative system is that a potential energy function must exist such that the force on the object can be written as the negative derivative of the potential function v with respect to the displacement coordinate. If it is not possible to do this, the system is not conservative. Note that we are still doing all of our work in one dimension, the x direction. Because of that, the force and the potential are functions only of the coordinate x, and both have a subscript x attached to indicate that the force and potential are due to the x coordinate only. We can rearrange this expression to give the differential of potential energy equal to the negative of the force times the differential displacement. If we want to obtain the potential energy function for a macroscopic displacement rather than an infinitesimal displacement, we integrate both sides from an initial position a to a final position b. Evaluating the integral on the left gives the potential at b minus the potential at a. If we leave the right side alone, this difference is equal to the negative of the integral of the force times displacement. The quantity on the right of the equal sign is the negative of the quantity we previously defined as work. This tells us that in a conservative system, the difference in potential energy of an object between a final and initial position must be equal to the negative of the work done to move the object from the initial to the final position. This is fairly important, so let's look at that in more detail. We have just learned that in a conservative system, the change in potential energy of an object when moving from point A to point B is the negative of the work done to move the object between those 2 points. We can multiply both sides by -1 so that we are left with work on the left side, and on the right side v of A, the initial potential energy, minus v of B, the final potential energy. We've also learned that in any system, the net work is the change in kinetic energy of the object in moving from point A to point B, which is expressed as the final kinetic energy, that at point B, minus the initial kinetic energy, which is that at point A. The left-hand side of these two expressions are the same, which means we can set the right sides equal to each other. This potential energy is at the end of the
stuff. Blah, blah, blah. Build on a Python physics library. Tutorial part 1.
Hello, in this tutorial I'm going to show you how to make a physics simulation in Pygame and PyMonk. And specifically, we are going to be making this. We have a blank screen with 2 dots, and if we click our mouse button, we are spawning an apple that falls down and is physically accurate. And we can go completely crazy with this and just drop a ton of apples, and they all fall down physically accurate. At least reasonably physically accurate. And yeah, that's pretty much it. Let's jump right in. And before we get into code, let's talk about the theory of what we are doing. And the most important thing we have to talk about is the PyMonk library. And the PyMonk library is basically a 2D physics library. So this one can help us to calculate physics in a 2D space. And this library could stand entirely by itself. So you could just run it, not visualize anything, but have all the accurate numbers to calculate some physics simulations. But what we are going to do for this tutorial is we take what's being calculated by PyMonk and then visualize all of this with Pygame. And you really have to be aware that those are 2 different libraries, and they are fairly independent of each other. So while we calculate the physics in PyMonk, we could visualize them in lots of other libraries. This could be Piglet, this could be Matplotlib, this could be Pygame Arcade. There are lots of different ways. Basically, anything that can visualize data could visualize the data from PyMonk. But in our case, we are using Pygame because it's a fairly straightforward library. And I do make the assumption that you already know some Pygame. It doesn't have to be much, just the absolute basics. If you don't know them, check out this video. It explains all the basics you need for this tutorial. But with all of that one done, let's talk about how to simulate stuff in PyMonk. And before we get into explaining anything, we have to install Pygame and PyMonk. So if you're on a Mac, open the terminal. If you're on Windows, open the PowerShell. And to install Pygame, you need pip install Pygame. To install PyMonk, you need pip install PyMonk. In both cases, you should be seeing a brief animation, and then you have it installed. This step should be fairly straightforward. And once
Let me install this before I continue. Even though probably not gonna use it. I forgot that I had some problems with Python using pip or VS Code. Maybe if I do the command prompt and I run Python. pip install. Yeah.
Once that is done, you can use them like any other library in Python. So you just need to type import and import the relevant module you want to have. Let's actually talk about how PyMonk works. The first thing we need for PyMonk is to create what is called a space. And a space is just an area where physics is being calculated. So we are basically creating a universe with our own physical laws. And the one physical law that is relevant for us in this case is gravity. So we create a space with a gravity. And also be aware, you have to continuously update this simulation. Otherwise, it's just standing still. And inside of this space, we can create physical objects. The first thing we need is a body. And the body is basically a physical body, with one major difference, that this body does not have a shape. So it can accept physics, but it cannot collide with anything. So we are basically controlling an atom right now. But to this body, we can get... And if you want to make sure that you install PyMonk correctly, just run the code now. And if you do not get an error message, you have installed all of the gravity. And this one needs a gravity both. And now we need how fast we want to update this. And in the PyMonk example, it's 1 divided by 50, so 0.02, which is a fairly small number. So effectively, we have two loops in our game. We have our game loop for Pygame when it updates the screen. And every time we update our screen, we are also updating our physics simulation. But you still have to be aware, we have effectively two different loops that could be updated independently. Now we have a basic simulation. If I run the code now, we still can't see anything because we haven't created any objects yet. And for that, I'm going to create a new function that I'm going to call create apple. And these are the apples I'm going to drop later. And for now, this one only needs one argument, and that's the space. So this space we created earlier. And inside of this function, we have to create two different objects. The first one is the body. And this is the atom that actually is being influenced by physics. And this is being created with pymonk.body. Spell it correctly. And there are different bodies that you can simulate in PyMonk. The easiest one is a static body. This one just doesn't move at all, and it's just a static body. So this one would not be moving. However, when moving bodies come in contact with it, they would be reacting towards them. So they still have impact on physics calculation. So when I showed you the example in the beginning, the circles at the bottom, those are static bodies because they don't move, but other physical bodies can still interact with them. The second kind of body is a dynamic body, and this is a body that can be moved. And these are the apples we have created earlier. And the third one is a kinematic body, and we are not going to create them in this tutorial. But basically what they do is that they can be controlled by the player or by some external code. Basically think of it like this. A kinematic body can move by itself and influence other objects. A dynamic body can only be influenced by outside objects, but it can still be moved. A static body just can't be moved at all. And in our case, our apples are going to be a dynamic body. And for this one, we need three different arguments. The first one is the mass of the object, the second one is the inertia, and then the third one is the actual body type, which in our case is dynamic. Mass should be the easiest one. It's basically how heavy the object is. Inertia means how difficult it is to get it to start moving. And you can calculate inertia in a more mathematical way. In our case, we're just going to use some random numbers and see what looks good. So for our mass, let's go with 1, and for inertia, I am just going to go with 100. So these are our first two arguments. Now to specify the body type. This will be done with the keyword argument body underscore type. And then we need pymonk.body.dynamic, all uppercase letters. So now we have an atom that can be influenced by physics. And the next thing we want to do is set the position of this atom.
Just trying to fix the Python thing here. This is not activating pip properly. See if this changes anything. I think I got it now. Maybe. think VS Code's not recognizing where Python is installed on my computer. I think I selected a different one. Let me see now. It works. It still doesn't work. I think I'm gonna look at the path. Let me change the screen. I'm gonna look at the environment path of the variable. And I'm gonna try to select again. It says you can find. So app data, local programs, Python. And the problem is not finding the variable. Maybe I'll do this later. I'll string. Let me try this command. Python -m vm .vm. You want to select it workspace folder? Yes. Let's see if now it works. Install Pygame. It doesn't work. Yeah, I don't know what's going on. issue site. Copy and paste instead on Python. I'll try this update, and if it doesn't work, just gonna continue and fix this later. The issue is I don't wanna reinstall everything because of the mating library. This has its own app data. Local. Programs. Scripts. So it says it's here. Bash Python can use a custom version of Python by modifying the setting to include the full path. This default setting is used as a fallback, no interpreted. That for the workspace extension will also not set. It's still activating on the wrong file. Maybe I have to delete the other virtual environment.
It is lockdown where I live, and there's nothing to do. So as a
So body dot position, and this again needs
I'll figure out this later.
to dribble,
Yes.
but now I'm going to set it at the middle of the screen, so x is going to be 400 and 0. So our screen is 800 by 800 pixels wide, and I'm going to set it at 400, so the middle of the horizontal space, and 0, so right at the top. So now we have an atom in one specific position, but it could not be interacting with anything because it's just an atom, it cannot collide with anything. To get it to collide with anything, we need a shape. And in our case, our shape is going to be a circle. So we are simplifying things quite a bit. And generally think of it like this. Calculating physics is really hard and math intensive. And when we later use our apple, it has a very irregular shape, which would be a nightmare to calculate. So what we do instead is we try to simplify the shape. And in our case, since the apple is fairly round, we just put a circle around the entire apple and simulate collision with this circle, which is going to make everything much simpler. But you could literally just draw a couple of points around the apple and make this much more accurate. So we need PyMonk.circle. And the circle needs two arguments. The first one is the body, so this line here, and then we need the radius of our circle.
Right back.
Which in my case, I am going to go with, let's say, 80. And this number we have to experiment a little bit with in a bit, because we have to make this as close to the apple as possible. So we basically
I
run
don't think I'm gonna use this library here, so I'm gonna close this video.
means of distraction from the fact that I have no redeeming qualities, I'm gonna take on the hardest coding challenge I could think of, an entire 3D physics engine. I haven't done 3D physics, but I've made another library before. In my earlier videos, I got a lot of comments asking me how I made the animations, and the answer is actually, I spent months and months writing my own graphics library. Basically, I looked at 3 Blue 1 Brown's animation library and thought, you know, I could probably do it better. That was a waste of time, but I'm bored, so let's do it again. Gonki, I hear you asking, what is this physics engine gonna include? Well, my friend, if I just... We're gonna do all the exciting simulations known to man. Soft body simulations? Check. I'm gonna start with soft bodies, in fact. I think it's probably the easiest one. Fluid sims? You bet we're gonna have... I don't know what happened to the resolution of the image. Cloth simulations, rigid bodies, you name it. I'm just gonna try to make this into one big sandbox with everything available. I actually have no idea how to do these things, but I'm sure we'll figure it out. Now, it's really important that I pick the right programming language. So for this project, I'm gonna go with Microsoft Visual Basic.
No, God, please, no!
I'm gonna use C# and OpenGL. I've never used C# before, and I haven't done anything 3D in OpenGL. So here's an epic montage. Really symmetrical with
I think this video is
all
gonna have
vertices being
anything useful, to be honest.
as it is to move on to collision detection. Collision was every bit as painful as it sounds, so I'm just going to put a massive time lapse here in an effort to share my experience of suffering with you. You know, as a community, perhaps the thing that unites us is the universal post-traumatic stress disorder we acquire from browsing too much Stack Overflow. Hopefully some university professor can stumble. Alright, take your time.
Hello everybody, my name is Chimo Neutron and welcome to my first ever YouTube video. In this tutorial we'll build a Python library called Planck that is focused on making Python physics graphs. I expect you to have some basic knowledge about Python, such as functions, for loops, but in this tutorial you'll learn more about Seaborn library, pandas, matplotlib, and a lot more. So I will be using Jupyter Lab for this tutorial, but you can use a simple text editor. Just know that Jupyter is usually faster in compiling code. So let's create a new notebook, and let's change the name to Planck. And in first block, we'll just define constants and import libraries. The first library we'll use is simply math for mathematics functions. Second one is matplotlib.yplot as PLT, and we'll use Seaborn as SNS. If you don't know, Seaborn library is used for drawing beautiful graphs. And finally, we'll use pandas as P. And pandas is used for better data cleaning and data manipulation. And also let's define the constant G, which is the gravitational acceleration, and it's equal to 9.81 approximately. Let's run this one, and let's see if there are any errors. So there are no errors, we can move on. The first function we'll create will be called motion graph, and this function will be simply graphing motions for us. So for example, let's start commenting. We'll have several arguments, and all arguments will be predefined. So first argument will be velocity equal to 0, and then we'll have s, which is distance, and time, which is also equal to 0. Let's define them all here. Oops. And lastly, we'll have a different argument called specify. Specify is a string, and it will be used from the user side to specify what type of graph they want to see. So let's go here and define specify and add several options here. For example, PT will be position time graph, VT will be
His typing is too loud.
graph, and lastly,
Yeah, I'm not gonna be able to watch this video. I think the best way is to start the playlist right away on Tensors and try to code and figure out the questions I have along the way.
Video series on tensors. In this first introductory video, I'm going to try and give you a bit of motivation for why you
I'm
might
gonna have to go very slow to make sure I'm understanding and trying to code this stuff.
study tensors, and then in later videos I'll get to explaining what tensors actually are. So before I start, I should mention that I expect people watching this video series to have a little bit of linear algebra under their belts already, so I'm hoping you already know how to multiply matrices and you know what terms like linear combination and dot product are. If you don't know any of this stuff, you're welcome to watch anyway, but you might find it a bit harder to keep up. What I'm going to try and avoid doing is doing any mention of calculus. Some people like to introduce tensors using calculus, but you really don't need that. You only need linear algebra. I'm going to talk a little bit about calculus and tensors at the end of the video series for people who do have a calculus background, but I'm going to do my best to avoid any mention of them until then. Alright, so why should we want to study tensors? So the main reason you would want to study tensors is geometry. If you understand tensors, then you can get a lot of insight into how geometry works. Now, I'm not talking about the geometry you would have learned in elementary school or high school, stuff like basic shapes or trigonometry. I'm talking about geometry that can be fairly complicated and not very intuitive. So one example of such geometry is the geometry of space-time in Einstein's general relativity. So let's talk about that a little bit. So if you've ever read or watched any popular science articles or videos on general relativity, you've probably heard about how space-time is curved and how light can travel in a curved path around massive bodies like stars and black holes. Another thing you might have heard about is how the universe is expanding, right? So at the beginning of time, we had the Big Bang here, and ever since then, the universe has been getting bigger and bigger, and so the universe is expanding. Now, when you first hear these ideas, you're probably thinking, you know, what the heck do these even mean? What does it mean for space-time to be curved? What does it mean for the universe to be expanding? So in order to understand these ideas mathematically, we need tensors. So I'm just going to throw up some equations on the board right now. So these are Einstein's field equations. And I say equations with an S on purpose because even though it doesn't look like it, there are actually 16 equations here. And these 16
I think a great idea is search for the derivation of Maxwell equations and code them. Maybe I can search for Python Maxwell equations. Code. Nice. Okay, so I'm gonna watch this video. So equations.
outcome.
I'm gonna watch this video and the other video side by side, I think.
Equations tell us how space-time is curved and why the universe is expanding. Now, you don't need to understand what any of these symbols mean, but the important thing that I'm going to point out to you is that every symbol that I'm underlining right now is actually a tensor. So there are tensors everywhere in these equations. And the most important tensor in general relativity is this one here, the g, which is called the metric tensor. It's a 4x4 rank 2 tensor, which you could also call a 4x4 matrix, and it helps us measure lengths and angles in the curved geometry of spacetime. Now, I'm going to talk about the metric tensor in, I think, video 7 or 8. I'm going to use much simpler examples than the ones you'd see in general relativity, but hopefully you'll understand what the metric tensor is, and you'll have taken the first few steps toward understanding why spacetime is curved and why the universe is expanding. All right, so another example of tensors being important is in quantum mechanics, and in particular, quantum computing. So quantum computing is a pretty active field of research these days. If we ever get quantum computers working, they'll be able to solve some problems that the classical computers we use today are not able to solve, or at least the classical computers we have today can't solve them very efficiently. Anyway, again, if you've ever seen popular science articles or videos on quantum mechanics, you've probably heard the term quantum superposition. And so this is the idea that quantum systems can be in two states at once. And usually they give some weird example involving a cat being dead and alive at the same time. I'm not sure how literally you want to take that, but there it is. And so another idea in quantum mechanics is the idea of quantum entanglement. And so this is the idea that two particles can become entangled, and even if you separate them by hundreds of kilometers, they can still influence each other in strange ways because they're connected using this strange quantum entanglement property. So again, what do these terms even mean? What's quantum superposition and what's quantum entanglement? What do these mean mathematically? So it turns out that superposition, if you know a little bit of linear algebra, superposition is just a fancy way of saying linear combination. So with linear combinations, what we do is we have what you might think of as simpler vectors, and we combine them together using scaling constants and addition to get a more complicated vector here. And it turns out in quantum mechanics, physical quantum states are actually just vectors. And so we can combine simpler states together using linear combinations to give us more complicated states. And so that's really all quantum superposition is. As for entanglement, when two quantum systems are entangled together, what we really mean is that the state vectors have been combined together using something called the tensor product. And that's what this circle X symbol is. It's the tensor product. So what the tensor product does is it takes the geometrical space where the first system lives and the geometrical space where the second system lives and combines them together to create a more complicated geometrical space. And that's where the entangled system lives. So I'll be talking about the tensor product in, I think, video 9 or 10. And hopefully that will be a first step toward understanding quantum entanglement mathematically. All right, so hopefully I've made you at least a little bit curious, and hopefully you want to learn a little bit more about what tensors are. In the next video, I'm going to start explaining what tensors actually are, and after that we can get started learning some actual math. So I'll see you in the next video. All right, so welcome to this second video in my series on tensors. In the last video, I tried to give you a few reasons for why you might want to learn about tensors. In this video, I'm going to try and explain what exactly tensors are. So tensors are a little hard to describe if you've never heard of them before. So what I'm going to do is I'm going to give you several different definitions that you might hear from different people when you ask them what a tensor is. And hopefully seeing all these different points of view will put you in a good starting position so that you feel comfortable when we actually start doing real math in the next video. Okay, so let's get started. Here's a first attempt at a definition for tensors. I'll just read it off. So a tensor is a multi-dimensional array of numbers. And by array, I basically just mean grid. So a grid of numbers. Okay, so let's see some examples of what this might look like. So the simplest example of a tensor is what we would call a scalar, or sometimes a rank 0 tensor. And a scalar is basically just a number. So any number like 1, 2, 5, 3/4, pi, these are all examples of scalars. And we don't normally write scalars as arrays, but if we wanted to, we could write little square brackets around the scalar like this and sort of pretend it's an array, but we don't normally do that. All right, so those are scalars. Another example of a tensor you've hopefully seen before is a vector, or a rank 1 tensor. And we call it a rank 1 tensor because it's a list of numbers that extends downward in one dimension. So it's like a one-dimensional array. So that's a vector. Another example you've probably heard of are matrices, or rank 2 tensors, and we call them rank 2 because they are a two-dimensional grid of numbers, so they extend up, down, left to right.
I think what I can create is a function that says vector. It takes n as an argument, which is going to be the number of dimensions of the vector. Then make the vector equals list. And vector dot appends. The issue is I would need to know which values are going to be in the vector. Yeah. Let's keep watching.
And if you recall from the last video, I mentioned that the metric tensor from general relativity is a rank 2 tensor. And these little Greek letters that you see here actually stand for numbers that represent the row and column of the particular entry of the matrix that we're talking about. So the metric tensor is really just a matrix. And we can go higher and higher. This is a rank 3 tensor because it's in a 3-dimensional grid of numbers sort of arranged in a cube. And we can go on and on, rank 4, 5, 6, as high as we want. So any multi-dimensional array of numbers is a tensor. So I call this the array definition of tensors. Okay, so I said that...
Thanks for the follow. See? Name is the dog. Yeah, my name is the dog. Thanks for the follow, man.
This was a first attempt at a definition, and it does give us some idea of what a tensor is, but this definition is actually wrong, and here's why. So tensors can be represented as multidimensional arrays, but that's not what they fundamentally are. Tensors aren't just a bunch of numbers that we toss together. Tensors actually have real geometrical meaning. And if we just think of tensors as these multidimensional arrays, we sort of miss out on the geometrical meaning behind them. So if we casually toss the word tensor around to mean a multidimensional array of numbers, you know, that's sort of fine. There's nothing wrong with that. But if we're thinking seriously like mathematicians and we want to understand geometry, this definition, the array definition, is simply just wrong. So it's no good to us. Okay, so let's try again. So here's another attempt at a definition. I'll just read it. A tensor is an object that is invariant under a change of coordinates and has components that change in a special predictable way under a change of coordinates. Okay, so that's certainly a mouthful. So what does that mean? So let's start with the top part. What does it mean to be invariant under a change of coordinates? Well, to explain that, I'd like you to try picking up a pencil and point the pencil toward the nearest door that you can see. So there are a few things that we can say about this pencil that are just facts, and they don't depend on any coordinate system. So for example, the length of the pencil, the length won't depend on our choice of coordinate system. The length is an intrinsic or invariant quantity. Also, this pencil is pointing toward the door, and that's just a fact. It doesn't depend on what coordinate system we use. The pencil's orientation is intrinsic or invariant under the choice of coordinate system. Now the second part, what does it mean for components to transform predictably under a change of coordinates? Well, to start off, let's introduce a coordinate system here. So we have a nice...
So basically the dimensions of the vector don't change in relationship to the different reference frames. That's why they're covariant. So if you increase the size of the coordinates, the vector is gonna decrease proportionally to the amount you increase in the coordinates in order to keep the proportions of the vector
3D coordinate
constant in relationship to different reference frames.
System with 3 vectors here that give us the main coordinate directions. And what we can do is we can measure the pencil using this coordinate system. All right, so it looks like this pencil is made up of 2 yellow arrows, 1 green arrow, and then 2 blue arrows. All right, so we can write this pencil as a linear combination of the coordinate vectors here. Okay, so what we just did here by breaking down the pencil into the coordinate vectors is we measured the pencil's components. The components are just the amount of each coordinate vector that we need to construct the pencil, right? So with this coordinate system, the components are 2, 1, 2. Now I introduced this coordinate system here, and you might think it's a pretty sensible coordinate system because all the direction vectors are the same length and they're all perpendicular to each other, so that's kind of nice. But really, there's nothing special about this coordinate system, right? I could just as easily introduce another coordinate system like this, where the vectors are all different lengths and they all sit at weird angles relative to each other. But mathematically, neither of these is more correct than another. They're simply just different choices. And so with this second coordinate system, I can sort of do the same thing. I can measure the pencil along each coordinate vector, and I can see that this pencil is made up of 2 black vectors, 3 purple vectors, and then 1 red vector. And again, I can write the pencil as a linear combination of these vectors, and I get the components 1, 3, 2. So you'll notice when I measure the pencil using different...
So I think the way I can do this function is by assigning arguments that are equal to the reference frame that I want to represent. But the issue then is that I'll be limited by the amount I choose. So I can make 3-dimensional vector 3D underscore vector. Well, I can't do that. That's the name of the function. Vector 3D maybe, yeah. So vector 3D, make x, y, z as arguments, and then make the dimensions of the NP array that outputs depending on the coordinate system that the thing has. So the question is how can I make this? It's gonna be x, y, z. I'll think about
different coordinate
after I
systems.
watch the
I
video.
actually get different components, right? And this is a really important idea. The pencil's components are not invariant, right? They change depending on the coordinate system they use. Okay, so the pencil is invariant, but the coordinates are not invariant. Okay, and again, that's a very important idea. So now it turns out that if we know how to change one coordinate system into another coordinate system, right? So if we know how to go back and forth between these two coordinate systems, then we should also be able to figure out how to change back and forth between these different sets of components. And this process of going back and forth between coordinate systems and components, that's what I'm going to call forward and backward transformations. And I'm going to talk about those in the next video. All right, so backing up, what a tensor is an object that is invariant. It doesn't depend on a coordinate system, but its components, which do depend on the coordinate system, change in some special predictable.
So I think I need a function that creates a tensor. That's number one. Then I need a function that translates tensors in relationship different reference frames. So I have to think about what do I need to pass into the function in order to create each tensor. And then I will think about how to design the function that translates the tensor depending on the reference frame.
Way that we can figure out using these forward and backward transformations. And this is what I'm going to call the coordinate definition of it.
So one thing that comes to mind is that the dimensions of the tensor will have to be equal to the dimensions of the translation of reference frames, maybe. Because I wouldn't be able to know if I have a 4-dimensional translation with a 3-dimensional vector. It's impossible to make this translation because the vector doesn't have the necessary dimensions, maybe.
A tensor. And this definition is actually pretty good. It does get to what the heart of a tensor is. It's an object that's invariant, but whose components change. But it turns out that we can come up with an even better definition. And so I'm going to switch to that one here. So here's our third final definition. I'm just going to read it off. A tensor is a collection of vectors and covectors combined together using the tensor product. So this definition ends up being really nice. It's really short and sweet. There's just one problem. If you've never studied tensors before, you may have heard of vectors, but you've probably never heard of a covector, and you've probably never heard of the tensor product. So the downside of this definition is that we need to put in a little bit of work before we can even understand what it means. But once we understand what all these things mean, it's actually a really simple definition. Tensors are just vectors and covectors combined together in different ways using this thing called the tensor product. So this is what I call the abstract definition of a tensor. So this is really the best definition of a tensor we can come up with, and I'll get to this definition later on in the video series once we have the basics down. All right, and I have a little bonus part here. So for those who do have a calculus background, I'm going to talk about how tensors pop up in calculus, and that's when we see tensors as partial derivatives and gradients that transform with the Jacobian matrix. So you can skip this section if you aren't feeling very strong with your calculus skills. It's an extreme.
Yeah. So the Keras TensorFlow. I should have I think I made a connection, but I just wasn't thinking about that. But it's probably is exactly the same thing actually. Deep learning, and which is very interesting.
Extremely interesting use of tensors, and it's very important for the curved geometry we might see in general relativity.
Because it means the same laws of physics probably apply. The same structure that is being used for deep learning and for quantum mechanics and general relativity. It's basically mapping out space-time relationship to flow of data, which is electromagnetic field.
But if you're not comfortable with calculus, you can feel free to skip over this part. All right, so this is sort of the end of the introduction. I spent the last two videos just sort of preparing your brain for what tensors are. In the next video, I'm actually going to start doing real math, and we're going to start with forward and backward transformations. So I will see you in the next one. Welcome to
So I think it's probably better to watch the other playlists before I watch this. So I learn how to code them before, and then follow along the videos to try to do with the libraries I build, try to do the manipulations that it talks about in the videos.
Hi everybody, welcome to a new PyTorch tutorial. In this video we are going to learn how to work with tensors, so how we can
So I'm going to watch these videos on tensors first, then the derivation of Maxwell equations and the coding of Maxwell equations, build the libraries, then we'll continue watching the Tensor for Beginners
tensors and some basic operations that we need. We will also learn how to convert from NumPy arrays to PyTorch tensors and vice versa. So let's start.
Creates tensor, reference frames, Maxwell equations. Back. In there.
So in PyTorch, everything is based on tensor operations. From NumPy, you probably know arrays and vectors, and now in PyTorch, everything is a tensor. So a tensor can have different dimensions, so it can be 1D, 2D, or even 3D, or have more dimensions. So let's create an empty tensor. So first of all, we import torch, of course, and then we say x equals torch.empty, and then we have to give it a size. So for example, if we just say 1, then this is like a scalar value. So let's print our tensor. So this will print an empty tensor, so the value is not initialized yet. And now we can change the size. So for example, if we say 3 here, then this is like a 1D vector with 3 elements. So now if we run this, we see 3 items in our tensor. And now we can also make it 2D. So for example, let's say the size is 2 by 3. So this is like a 2D matrix. So now I'll run this. And of course, we can put even more dimensions in it. So now it would be 3D. And now, for example, now it would be 4D. But now I don't print it anymore because it's hard to see the 4 dimensions. But yeah, this is how we can create an empty tensor. And we can also, for example, create a...
Another thing that I also have to look at, I think even before I look at this stuff, I want to be able to see where the functions are coming from.
Hey there, how's it going?
I think I'm gonna use PyCharm for now because VS Code's not being able to recognize the Python environment. So I'm gonna change to PyCharm, which I didn't want to do because I have another project on PyCharm. But I guess it's fine. Just change the folder that I'm working on. So I'm opening the folder PyCharm. That I have separated for this stuff. Tensor, this window.
On everybody. In this video, we'll be learning how to import modules. We'll start by importing modules that we've written, and then we'll explore a bit of the standard library and how we can import those modules to solve a lot of common problems. So I have a module here called mymodule.py. Now, within this module, we have a print statement, and we'll talk about that in just a minute. We also have this test variable set to test string, and then we have this function called findIndex. And this findIndex function takes in 2 arguments. It takes in a list to search and a target that we're looking for. And we can see that we have some documentation here that just says that this finds the index of a value in a sequence, and then it returns that index. But if it doesn't find that value, then it just returns -1. So let's say that we wrote this function and that we want to use this in other modules or scripts. So what we're going to want to do is import this. So I have another module over here, which is just our intro.py file that we've been working with. Now within this file, we have this courses variable that is just a list of course names. So let's say that we want to use that findIndex function from my module. Now I actually created this my module in the same directory as my intro.py. So that means that we're going to be able to directly import that. Now when we import a file, it actually runs all of the code from the module that we import. So that's how it creates all of the functions and variables. But if we have any other code like print statements or anything like that, then that will be run as well. So that's why I have the print statement here in my mod is the index of the math value. Okay, so if we're using this find import, and then what we want to import from that module. So we want to import find index. So now when we use this throughout the code, now we can just use that find index function anywhere, and that really cuts down on the typing. So now we can save that and run it and see that it still works. Now, one thing to note about that approach is that it only gives us access to that find index function and not everything else in the module keyword. So if we wanted to is because now we can't tell what came from that and import, and it looks in this order. Now, this first value here is just the directory where I'm currently running the script from, and the my module Python file that we were importing is within that directory also, so that's the module that we've been importing from the same directory. Instead, we can make this change in the next place sys.path that location, and see that after our machine. So let's hit OK there and OK to save those and exit out of that. And now if we open up our command prompt by going to start run cmd and then typing in Python, and now we should be able to import that module just by saying import my module. And if we run that, then we can see that it imported that module successfully. Now the reason that worked is because if we import sys and look at our sys.path, then after our current directory, you can see that our directory that we added to our Python path.
I'm gonna have to change Python launcher because PyCharm is not working.
Hi there, Serdar Yeguloup here for InfoWorld at IDG. Today I'm going to demonstrate the Pi launcher for Python under Microsoft Windows. The Pi launcher is a utility typically installed by default with Python in Windows that lets you quickly select and launch a version of Python if you have more than one Python instance installed. On this system here, for instance, I have 3 distinct versions of Python installed: 3.7, 3.8, and the beta of 3.9. I use all 3 of them for different things: 3.7 for apps that need the broadest possible compatibility, 3.8 for current development, and 3.9 for bleeding edge testing. The Pi launcher lets me run any of these from the command line without needing to know their full path. You can just type Pi to launch the default version of Python, like this. Or you can use a command line switch to launch another installed version of Python. For instance, to launch 3.7, I'd use pi-3.7. And likewise for Python 3.9, pi-3.9. Any command line arguments you pass after the version number are just passed along as is. For instance, to invoke pip, I type pi-3.7-m pip. If you don't pass along a version number, then Pi will just launch the default instance of Python, and again it will pass along whatever other command line arguments you've typed. If you want to see at a glance which Pythons are installed in your system, type pi-0 and you'll get a list. The entry marked with an asterisk is the default. Now what if you want to change the default? Well, the easy way to do this is by way of an environment variable, pi_python. Set that to the version number you want to invoke as default. So in PowerShell you type this command. Now as you can see, 3.7 is the default. Note that we only set the environment variable for this session though. Here in another session, you can see that 3.8 is still the default. If we wanted to make this change permanent, we'd need to edit the user environment variable setting, as shown here. Finally,
maybe I have to delete a variable. Not sure if I can show this on stream, but Python scripts. Maybe now it will work. Gonna reinitiate PyCharm. I had a path environment variable for another hard drive and setup. Not find a version that satisfied the requirement torch from versions. No. No mesh. Let me see, pi 0. Not find a version satisfy the requirement. So apparently it fixed the problem, but
If you're in a virtual environment, Pi will by default use the virtual environment's Python. But if you specify one of the other Python installations manually, it will use them.
If you have questions, please add a comment below. Don't forget.
let's see how to install torch. This is the most annoying part of programming. Setting up all this stuff. Maybe there's PyTorch instead of torch. Yeah, now it seems to be working, but yeah, it's not finding the. Let me show. I don't think it's finding the correct Python file. Or maybe it's just torch, like it says there. Not find a version that satisfies the requirement torch. Yeah, it should be with the way that. I think now it's gonna work. I changed the interpreter. Apply. Okay. Could not find a version that satisfies the requirement. So is the version. Three-point down. Let me try the commands it shows there.
Hello friends, welcome back. My name is Rahul Kumar Sinha, and in today's video we are going to see how to install PyTorch library in Windows 10. First, navigate to the official website of PyTorch, that is pytorch.org. For all those who don't know about PyTorch, it is an open source machine learning framework mostly used for deep learning. Now, as the website is opened, scroll down where we can see few key features and capabilities of PyTorch. Scroll further. This is a section menu where we can select preference according to our system requirement. And here, the website will populate the installation command according to our selection. On the right side, we can see PyTorch is also available for different cloud platforms like Alibaba, AWS, GCP, and Microsoft Azure. But today, as we are installing it on a local system, hence we will use the left side selection menu to populate the installation command for us. Regarding PyTorch build, there are two options, stable and preview or nightly. PyTorch is an open source library and keeps updating at regular intervals. Preview or nightly is a beta version of the project that may have few bugs in it. So we will select the stable version of PyTorch. Then I'm selecting Windows.
So apparently it's not supported by Python 3.10. Okay. Let's try this command. I find a version that satisfies the requirement. Torch was one from version unknown. I'm not sure if this problem is the way that PyCharm is interpreting my stuff. It says requirement already satisfied, but on the file it says no module name numpy. I changed the interpreter again, let's see if it works. If it doesn't work, I'm gonna have to see how to install Python 3.8 and then change the interpreter. It's gonna be a pain in the ass.
And I will use the default pip tool that comes with the Python language. The language is Python. CUDA is the option for GPU system. According to the version of GPU or GPU version, you need to select the CUDA version. I don't have GPU in this system, hence I will select none. We'll copy the command and open in command prompt. Activate the environment using command script activate and paste the command that we have copied from the website. That's all we need to do. PyTorch will be downloaded and installed. It was a pretty big file. It takes a lot amount of time depending upon your internet speed. But as the installation is complete, Let us verify the installation. For that, I'm just going to get into Python interpreter, typing Python, and importing the torch module. I'm just creating a random torch variable, which is a tensor of 5 cross 3. Trying to print that tensor, and here is our tensor. If you are using a GPU and you have installed the GPU version, you can verify for the GPU installation using the command torch.cuda.is_available. For me, it's showing false as I have not installed the GPU version. For you, it will show true or false depending upon your GPU version you have installed. Thanks for watching.
So I think what I'm gonna do is search for Tensors Python 3.10.
Is the second one that it looks at here. So that is how we add that environment variable on Windows. So now I'll switch. Hey everyone, it's Dan, and in this video I want to talk about how you can figure out what a Python package or Python module has to offer. So imagine you're working with a brand new Python module, maybe one that you installed off the internet or one that was included in the Python standard library, and you want to find out how to use it. What does this package offer to you? What methods does it have? What classes does it have? And how do you find that out, and how do you work with a brand new package? This is what we're going to cover in this video. So there are a couple of ways you can approach this problem. And I'm going to show you one or two that involve the command line. So this is what I have open here. And there's also one that involves browsing on the internet. If you like that better, we're going to cover that at the end of the video. So let's jump right into the command line approach. We're going to find out how you can inspect a Python module. The first thing that I'm going to do is I'm going to install a popular Python library called requests. And you can see here in this terminal session, I have an activated virtual environment. So a virtual environment is kind of a sandbox to keep your Python, or to keep third-party Python code that you install, third-party modules that you install, completely separated from your system Python install. And this is going to help you avoid version conflicts, and it's going to help you just keep a nice and pristine system environment while still having the ability to experiment and to install different versions of the same package at the same time. So this is a little bit complicated if you've never done it before, but there's a link in the description where you can learn more about how to work with virtual environments and kind of the whole managing Python dependencies, workflows, and skills that you would need around that. All right, so what I'm going to do here now, because it's really not the scope of the video, we're going to install the request library. In this case, I already had it installed, but you would have to run this pip install request command to install it locally. And then I'm just going to boot up the Python interpreter, and I'm going to go ahead and import this module. So now we've imported it. You can see here, successfully imported this module. So now the big question is, what does this request library actually offer me in terms of functionality, in terms of its public interface, in terms of how can I access the classes inside, what constants are there inside, what functions can I call? And for that, you can use the dir function in Python. So I'm just going to go and call dir. So maybe just show you that first. So dir is a built-in function that's built into Python. And I can just point it at any module, or any object really, and it's going to tell me the symbols and the names that this module exports. So that was actually pretty interesting, right? Because now I can kind of explore this request module. And as you can see here, there's a bunch of interesting stuff in here. So if we wanted to inspect one of them, for example, the HTTP error here, then we could do the same thing again. You know, we could drill down and kind of get a sense for maybe what this HTTP error does. But maybe actually a better approach here would be to use the built-in help function. So in this case, you can use the built-in help function on a class. And what this will do is it's going to bring up this full screen view of. And there's one more trick.
But I want to see on the
HTTP error in there earlier on, right?
file itself, not on the command line.
Particular class or name or object or whatever it is. And yeah, the basic use case here is the Anaconda plugin. Matter of fact, you probably should. They kind of tell you how to use the library to tell you what's available here. And this is made for human consumption. So someone specifically sat down and wrote this user guide. Most of the times, a good library will have something like a quick start guide that you can click through, and you can kind of inspect that, or you can read that. And what you example here, and it tells us
maybe they'll make it accessible. But
it makes a lot of sense to try and find if
otherwise you wouldn't use the API. But I'm not sure that's correct. So it seems like the only way is to use this library, which is PyTorch, which means I will have to install an earlier version of Python and create a virtual environment, and then use that earlier version on the virtual environment for the project.
Hello everyone and welcome to this interesting session on installed TensorFlow. So deep learning is one of the hottest topic of 2019 and 20 and for a good reason. Now the advancements in this industry has made it possible for the machines or the computer programs to actually replace the human beings. Can you believe that? And artificial intelligence is going to create 2.3 million jobs by 2020. And a lot of this is being made possible by TensorFlow, which can be considered as the big daddy of deep learning frameworks. So in this session, first of all, I'll give you a brief about what exactly is TensorFlow. We'll understand how TensorFlow has helped a lot of companies build world-class models and solve real-life problems. And finally, we'll cut through the chase and I'll explain you guys how to install TensorFlow step by step. So TensorFlow is Google's open source machine learning framework for data flow programming across a range of tasks. Now, if we talk about data flow, there are nodes and graphs involved. So nodes in the graph represent mathematical operations, while the graph edges represent the multidimensional data arrays communicating between them. Now, these multidimensional arrays in terms of deep learning are known as tensors, and it is an extension of 2D table to a data with a higher dimension. But there are many features of TensorFlow which makes it appropriate for deep learning, and the core open source library helps you develop and train machine learning models. Now, TensorFlow has helped a lot of companies build world-class models to solve real-life problems. So, for example, if we take Airbnb improves their guest experience by using TensorFlow to classify images and detect objects at a scale. And if we talk about Coca-Cola, so the advancements in the artificial intelligence and the maturity of TensorFlow enabled Coca-Cola to finally achieve a long-sought frictionless proof of purchase. And TensorFlow has made a lot of advancements in the healthcare industries as well. So GE, which is GE Healthcare. So using TensorFlow, GE Healthcare is training a neural network to identify specific anatomy during the brain magnetic resonance imaging, which is MRI exams, to help improve the speed and reliability. As you can see here, we have the system requirements. So let's go to the pip installation page. And here you can see in system requirements, we have Ubuntu 16.4 or later. We have Mac OS 10.2, which is 64-bit again. Then we have Windows 7 for Windows and Raspbian 9.0 or later for Raspberry Pi. Now, I'm not going to go into the details of the GPU support because if I click on the GPU support guide, it requires you to have CUDA enabled GPU as well as it requires you to have a TensorFlow Docker image with GPU support. All you need to do is provide the command pip install TensorFlow-GPU. So as you can see here, it requires a TensorFlow Docker image with GPU support that is only for Linux, and it also requires an NVIDIA GPU. So first of all, the first and the foremost step is to get Python. So under Python, as you can see here, I'm going to take the version 3.7.3 and I'm going to use the executable installer. I've already downloaded it. Let me run it for you. So all you need to do is select the add Python and add Python to the path and just click on the install now because this is a very important step. So guys, it's going to take around 3 to 4 minutes to initialize and get the installation done. So after that, what you need to do is install pip. So, but what happens is that in Python 3.5 and above versions, pip is already there. So you do not need to install it separately. And the next thing what you need to do is get the virtual environment, which is the virtual env. So for that, what you need to do is just use the command pip install virtual env and the virtual environment will be done. What happens is that in Python 3.5 and above versions, pip is already there. So you do not need to install it separately. And the next thing what you need to do is get the virtual environment, which is the virtual env. So for that, what you need to do is just use the command pip install virtual env and the virtual environment will be done. Let me check up on the setup progress. I think it's almost done, 50% of it.
But how do you do that?
To classify images and detect objects at scale. And if you talk about Coca-Cola, so the advancements in the artificial intelligence and the maturity of TensorFlow enabled Coca-Cola to finally achieve a long-sought frictionless proof of purchase. And TensorFlow has made a lot of advancements in the healthcare industries as well. So resonance image, Twitter is their most important. 3 steps. As you can see here, we have the system requirements. So let's go to the pip installation page. And here you can see in system requirements, we have Ubuntu 16.4 or later. We have Mac OS 10.
Check if your Python environment is already configured. So it shows a mistake for mine. But pip is showing that 3.10. So let me create this virtual environment. So apparently it worked. Now activate it. Whatever. Choose one of the following TensorFlow packages from install from pip. Pip install upgrades. Yeah, it's saying the same thing. Do not find a version that satisfies the requirement TensorFlow. Versions none. No match distribution found for TensorFlow. So it must be that there isn't a version for Python 3.10.
Which is 64-bit again. Then we have Windows 7 for Windows and Raspbian 9.0 or later for Raspberry Pi. Now I'm not going to go into the details of the GPU support because if I click on the GPU support guide, it requires you to have CUDA enabled GPU as well as it requires you to have a TensorFlow Docker image with GPU support. All you need to do is provide the command pip install TensorFlow-GPU. So as you can see here, it requires a TensorFlow Docker image with GPU support that is only for Linux, and it also requires an NVIDIA GPU. So first of all, the first and the foremost,
I'm gonna do this off stream. And then next time I come back with everything prepared. Hopefully. The thing that I'm sure about as well is the manning library. If I reinstall Python, or if I install an earlier version of Python, how the manning installation is gonna work. But then maybe I'll do the TensorFlow stuff first and build the libraries and everything, and then I try to see how it's gonna work with manning. But I'll do this off stream, and I might come back today, but probably tomorrow or some other day to continue this Kaggle courses and continue this project. So see you.